everybody. I'm Umemura1 from Tokyo University, Sendai, Japan. Going to talk about ultrasonic imaging for high-intensity focused ultrasound treatment. There are two modalities to guide HIFU treatment: ultrasonic imaging and MRI. Ultrasound has its strengths in natural self-correction between imaging and therapeutic beams, real-time capability, relatively low cost, and portability. MRI, on the other hand, has its strength in the ability to map tissue temperature. Compared to this, ultrasound has its difficulty to detect tissue change unless cavitation and/or boiling occurs. However, Dr. Uchida of Tokai University is using this boiling event to control the tissue temperature in his clinical treatment of prostate. Dr. Uchida is using an ultrasound-guided transrectal HIFU treatment machine which Narendra Sanghvi had developed. This is the display he is watching during his clinical HIFU treatment. In the image on the right, the area being painted in orange, boiling echoes are seen. Here, Dr. Uchida was carefully adjusting the driving voltage so that he could see slight boiling in the focal zone at each HIFU shot. In other words, HIFU intensity was being adjusted so that the focal peak temperature should reach 100 degrees at the last moment of each HIFU shot. Then what was the temperature distribution created by the HIFU exposure sequence? The tissue temperature distribution can be calculated by numerically solving a bioheat transfer equation using prior knowledge of the process tissue and HIFU transducer. Here is the temperature distribution a second after the start of the first HIFU shot. 2 seconds, 3 seconds, the HIFU transfer is turned off after this. 4 seconds, 5 seconds, and 6 seconds, the HIFU focus was laterally shifted by 3 millimeters and the HIFU transducer is turned on again. And HIFU exposure continues in the same way. It continues, continues. This is the temperature distribution 30 seconds after the start of the HIFU exposure. This shows the temporal maximum temperature at each point of the tissue, and this shows the thermal dose at each point of the tissue calculated from its temperature history. You can see a contiguous thermal coagulation volume has been created. Conclusion up to here: ultrasound can easily detect boiling events. Using the boiling detection capability in combination with thermal simulation based on a bioheat transfer equation using prior knowledge of the tissue to be treated, HIFU-induced thermal coagulation can be predicted with the accuracy needed for certain clinical practice. Yeah. I said ultrasound has its difficulty to detect tissue change unless cavitation and/or boiling occurs. However, it's possible. What kind of tissue change should be monitored during HIFU treatment? The temperature elevation in target and no-target tissues, like MRI shows, or the thermocoagulation of target tissue itself. Then what can ultrasound can detect during HIFU treatment? This is the list of pioneering studies detecting such tissue changes. Thermocoagulation of target tissue and temperature elevation in target and no-target tissues. Okay. Here, I would like to show our study to detect thermocoagulation of target tissue during HIFU treatment. This slide shows the experiment. HIFU was generated from the focus transducer at 1.13 MHz. A person's liver tissue was exposed to HIFU at 1.5 kmol per square centimeter, which is measured in water. Ultrasound RF echo data acquired with a probe at 10 MHz. The HIFU-induced coagulation of tissue was detected as you see. This is the algorithm used to detect the tissue coagulation. This is a kind of block matching algorithm which is widely used to detect motion between frames. It searches a block with maximum correlation coefficient. Without tissue change, maximum should be close to 1. However, when the tissue changes, the value should be significantly less than 1. By two-dimensionally plotting the value, you can have a map showing tissue change. In high-speed imaging, unlike conventional imaging, unfocused transmission beams are used in combination with parallel reception beamforming. Coherent compound imaging can be employed to improve its contrast resolution. Can high-speed imaging further improve the performance to detect the tissue change due to HIFU? This is the experimental setup to detect tissue motion due to radiation force from HIFU. This shows the tissue displacement immediately after HIFU exposure in focal zone in millimeter. Since the acquisition time for a frame in conventional imaging is about 30 milliseconds, you need to wait for not less than 50 milliseconds after the end of HIFU exposure. It requires an intermission in the order of 100 milliseconds during HIFU exposure. In contrast, the acquisition time for a frame in high-speed imaging is only a millisecond. You don't need to wait after the end of HIFU exposure. It requires an intermission in the order of only a millisecond during HIFU exposure. This is a typical sequence of HIFU exposure and RF echo data acquisition for high-speed imaging. Here, the HIFU exposure duration is more than 97%. Okay. And this is the obtained map of decoration between adjacent frames. Tissue coagulation seems to have started about 7 seconds after the start of HIFU exposure and almost ended 10 seconds after the start. This is its minimum hole map, presumably showing the area of thermal coagulation. The decoration area is about twice larger than the actual HIFU coagulation. Probably because the tissue slightly shrunk due to thermal coagulation, and it forced the surrounding tissue to slightly expand, as seen in its EMT-stained histology. Another application of high-speed ultrasonic imaging. An effective hyperfocal zone can be shifted and deformed due to the spatial differences in speed of sound and ultrasonic absorption, as well as nonlinear absorption. Therefore, visualization of effective focal zone in advance is needed for targeting hyperfocus and prediction of thermal lesion formation. An acoustic radiation force impulse is known to induce tissue deformation, which can be detected by high-speed ultrasonic imaging. Acoustic radiation force acting on tissue is proportional to the acoustic intensity component attenuated by the tissue. Acoustic heat deposition on the tissue, on the other hand, is proportional to the acoustic intensity absorbed by the tissue. Therefore, the radiation force can predict the heat deposition if you can ignore the radiation force due to back scattering. In other words, the points of action of radiation force is approximately the same as the heat source. This shows the tissue displacement induced by a short hyperpulse for 2 milliseconds at the same intensity that the tissue was coagulated by a 7-second exposure as shown here. The points of action of the high radiation force are hard to see because the shear wave propagation blurs them. However, points of action of the high radiation force can be restored by backtracking the displacement, as you see here. Since it is difficult to detect the displacement during the high pulse due to interference, the displacement was backtracked through simple linear approximation at each point of the tissue. The restored points of action of the high radiation force well predicted the effective hyperfocal zone. In conclusion, using the borrowing detection capability of ultrasonic imaging in combination with thermal simulation based on a bioheat transfer equation using prior knowledge of the tissue to be treated, hyper-induced thermal coagulation can be predicted with the accuracy needed for certain clinical practice. High-speed ultrasonic imaging will be effective to guide clinical hypertreatment in the near future in real-time detection of thermal coagulation of tissue using declaration of the RF echo signals and prediction of the shift and deformation of an effective hyperfocal zone. Thank you.